Okay, so we're on our vectors topic. This is example 19. We've had a look at equations of lines and planes. We've had a look at the angles of intersection. Now we're going to have a look at points of intersection, certainly of lines. How do we work out or find out where lines intersect? Well, we use exactly the same algebraic strategy as we've used all along when we were trying to work out where two lines intersect in 2 dimensions, or a line in a circle, or a line in a curve. And that is, if you have, say, the equation of a line and, say, the equation of a curve, then what we can do is substitute the equations, make one equation out of two, substitute one equation into the other. So if, in this case here on the left-hand side, if y is 2x plus 1, then I can substitute that into the other equation, and we get 2 plus 1 equals x squared. And we can solve for x. Similarly, if we've got a circle in a line, we can substitute the equation of the line into the circle and solve for x. In other words, finding the points of intersection is always about effectively substituting what we know, creating simultaneous equations effectively. You're trying to substitute into one function into the other. So what have we got to substitute into? Well, we don't have any way really of doing anything with these lines, but what we can do is rewrite the lines in parametric form, and that's the way in which we get equations that we can play with. So in line 1 here, we can, this line here, we can rearrange. Remember that these Cartesian equations have always, with a different colour, we can write at the end of the fraction equals some parameter, sometimes t, or another letter. I'm going to call them u and v. Okay, that's going to use that as my two parameters, u and v. So in that case there, we can say that the set of equations that we've got is x plus 4 equals 2u, therefore x equals 2u minus 4. And they've also got y minus 5 equals negative 4u, therefore y equals negative 4u plus 5. And in my z coordinate, z minus 3 equals 1 times u, so z equals u plus 3. So here we have our 3 parametric equations based on line 1. And we can do the same for line 2. We can say that x is equal to negative v. So that's it. I've got nothing else to rearrange. I can say that y minus 3 equals negative v, so y is equal to negative v plus 3. And the third one, z minus 2 equals v, so z equals v plus 2. So what I've got here then are my 3 parametric equations for line 2. So how do we make our equations that we can solve simultaneously? Where's the substitution that's going to happen? Well, effectively we can say that at the point of intersection, the x coordinates have to be the same and the y coordinates have to be the same. That's the whole point of equating one function with another, because at the point of intersection, the two equations have to be the same. So what we can do is that we can create some new equations. So we can say here, at the point of intersection, I'll use POI. We can say x1 is equal to x2, y1 has to be equal to y2. That's of the effect of the equations of lines 1 and 2, and z1 equals, it has to be z2. That's effectively going on the basis that we call these x1, y1, z1. Okay? In other words, my new equations become 2u minus 4 equals negative v. And then equating the y equations, negative 4u plus 5 equals negative v plus 3, and then equating the z terms, u plus 3 is equal to v plus 2. Okay, so I've created from the two sets of parametric equations, I've created 3 new equations. Now, I've got 3 equations with 2 unknowns. So in order to solve for u and v, I really only need to pick 2 of them. Okay, so the idea is that if we call that equation 1, 2, and 3, we need to pick 2 of them to find u and v, and we're going to use the third one, the one we didn't use, to basically do a check that actually the solution is correct. So you can pick any of them, it doesn't matter. I'm going to pick which one shall I pick? It's always good to try and pick one where you can easily rearrange it. Like for instance 3 here is quite easy to rearrange just in terms of one letter in terms of the other. So if u plus 3 is equal to v plus 2, then u is equal to v plus 2 minus 3, so u is equal to v minus 1. And that's a good one to substitute into number 1. So we're going to use equation 3 and equation 1. We can say that u is v minus 1 and 2u minus 4 equals negative v. So substituting in, we can say that 2 times v minus 1 minus 4 equals negative v. That's what I've done there, is I've taken the v minus 1 and I've put it in there for u. Multiplying out, 2v minus 2 minus 4 equals negative v. Adding v to both sides, 3v minus 6 equals 0. 3v equals 6, so v has a value of 2. And substituting, if v is equal to 2, then u, which we know is v minus 1, has to be 2 minus 1, which is 1. So according to our strategy here, having picked 2 of the equations, I rearranged 1 so that it worked quite well for substituting. You can use the elimination method if it doesn't work out very well, but here we've got one that lends itself quite well to rearranging, and I've substituted it into equation 1, and I've worked out that v is 2 and u is 1. Okay, now it's really important that we don't just say, oh well, that's the answer. For a start, it's not, but also what we've got to do is to take the one that we have missed out. So that's equation 2. We have not used equation 2 to derive the values of u and v, so we use that to check. Okay, so let's bring up a wee check. Check with equation 2. Equation 2 says negative 4u plus 5 equals negative v plus 3. So let's check the left-hand side. The left-hand side is negative 4 times 1. So it's negative 4 plus 5, which is 1. Let's check the right-hand side. Negative v plus 3 is negative 2 plus 3, which is 1. So we can say the left-hand side is equal to the right-hand side. So what have we found out? So basically we can say that the values are consistent. For a start, we can say that L1 and L2 intersect. Okay? So that's an important thing. In order to prove that it intersects, we've got to actually, I'll rewrite that. So L1 and L2 intersect. Am I asked to prove that it intersects? Let's just check. Way back, prove that the lines L1 and L to intersect. So we have proved that it intersects by showing that there's a common value of u and v for all of the equations. Okay? That common value, i.e. u equals 1 and v equals 2 for all equations. And if we know the values of u and v, we can go back up to our original parametric equations. Seems like a while back, okay? We can go back to our original parametric equations. We can pick either, set either the line 1 equations or the line 2 equations, and we can actually find out what those x, y, and z values are, okay? So what we got for our equations, we can say coordinates. The original x coordinates for line 1 is -4 u, what was it? Negative, oops, 2u minus 4. X equals, I'm looking at the wrong one. X equals 2u minus 4. So therefore, x is going to be 2 minus 4, which is -2. The y coordinate was -4u plus 5, which is what the use was. So it's -4 plus 5, which is 1. And the z equation was u plus 3, which would be 1 plus 3, which is 4. In other words, the point of intersection is the point -2, 1, 4. Okay, so there's actually quite a lot of working out in all of that, and it's really important that every stage is done. Let's just recap on it. So we've taken our two lines in symmetric form, we've rearranged them into parametric form so that we can kind of take from them each of the individual equations. We have merged the matching x, y, and z equations to form 3 new equations in terms of both u and v. We then take 2 of the 3 equations and solve them simultaneously to get values for u and v. And we then use the third equation to check that those u and v values are consistent with the third remaining equation. If that is true, then we can conclude that indeed the lines do intersect. You can get matching values for u and v for 2 of the equations. That's not that's very common, but it doesn't work with the third one. In other words, it's not consistent for them all. So it's really important that you do that extra check. And once you've confirmed u and v for all the equations, we can substitute in to actually get our point of intersection of the 2 lines. Okay, so a bit of detail there. Just make sure you get all those different points and try it yourself.